Okay. Okay, I think that we can start slowly as people are coming in. So, I mean, today is gonna do the starting point of calculus variation. You're gonna see that some of the first parts are quite familiar to you. I'm starting anew. We are covering from the beginning, and then we're gonna go very deep to study about existence. So, I mean, maybe let me write out the basic goals. Here is gonna be, existence minimizers, or in general, it could be just extremal curves. Extremal curves. In calculus variation, people can say extremal curves are essentially critical points. And the second basic goal gonna be, we're gonna study regularity of minimizers, also of extremal curves. And later on, the more sort of like more modern viewpoint, calculus of variations, the classical viewpoints are only concerning those, existence and then regularity. Sometimes you might have uniqueness, sometimes you might not have it. But then the modern viewpoint is going to be about, the dynamical properties of minimizers or extreme curves. So those gonna be more of our focus, but because we're gonna do it from the beginning, so I'm gonna take it slowly. I'll explain to you what do I mean by that. But I mean, it's actually good if you already knew this part, you can take it slowly and maybe enjoy it. Just like have a good review. So again, this is sort of okay. The reference for this, reference for this can be the classical text can be Evans, the PD book, chapter 3. This has a little bit of that, and then the chapter 8 or something on calculus of variations, on calculus of variation. Okay, and then surely Fatih's book. It is he has done it quite carefully, and then our lecture notes. There is a simpler setting. You can also see in my book. There was in the appendix. There's a simpler proof about existence and regularity for the simpler setting. I'm gonna do it more, more advanced here. I'm gonna tell you, we're gonna go to the very general setting. Okay, so let's start. Again, we recall that this is a Lagrangian, and X represents for positions and V represents for velocity. Of course, you can see that we are only dealing with curves here. For general calculus of variation problems, it could be a functions or a vector value functions. Here, we only dealt with curves. We're gonna deal with two settings, either L maps from Rn times Rn to R. So it's a whole domain. And later on, for our purposes, we're gonna deal with the settings that, I mean, this is gonna be a more relevant setting later on, where R is mapping from the torus cross Rn to R. So here X stands, X stays in the torus. Okay, so I would say that the more relevant setting for us, the more relevant setting for us later on, gonna be X stays in the torus, which is Rn mod Zn. So this is a compact manifold setting. You can see that in Fatih's book, all of this can be done for a bit more general compact manifold, but it just, modulo a lot more of difficult technicalities. The idea is going to be the same, whether I'm doing it for the torus or for the more general compact manifold. So I prefer to stay in the torus, so that's going to be the more relevant setting for us. Okay. So I mean, this is going to be later on when we're going to deal with Tn, will be the setting. Let's say that for at least 2/3 or half the course later on, that we're going to deal with the compact manifold, which is just the torus. Okay. So that's the more relevant setting later on. So so our problem here is that our problem is that we fixed a less than b between which are integers, so they are fixed numbers. So basically the interval of integration is fixed first. So the functions, the action functional we care about is this I of gamma, and I'll tell you later on what we really care about. So let me just write it down again. So I of gamma is called action functional. It's integral from A to B L of gamma s, gamma dot s ds. So I is called action functional because you take a function gamma, you map it to I of gamma, which spits out in a real number. So we call it action functional. It's not a function, it's a functional. So this is called the action of gamma for L. And as I said, we're gonna go from a very basic baby settings to a more general setting. So for now, we just deal with gamma that is, let's say, piecewise, that is continuous, and piecewise C1 curves. Okay, so as I said, we're gonna start from the very beginning until a more general setting. So bear with me if you feel that this is not natural. I will explain to you why. But I mean, for now, the curves we are dealing with are just, like basically you have this is gamma of A. This is gamma of B. Your curve is pretty nice. It's sort of piecewise C1. So each of the pieces C1, it can have, jump in the gradient at a finite number of points, but this is your piecewise C1 curve. And if you deal with piecewise C1 curve, then the integral is defined in a very simple, like Riemann setting, right? So it's just a Riemann integral. There's no big deal about that. So so later on, we're gonna deal with gamma, which is absolutely continuous. Okay, so that's going to be a more general setting later on. Or you can think of it as sort of like basically L1. Okay, it's a little bit different, but you can think of it that way. Okay, So we're gonna deal with a problem that you fix the two endpoints. Um, so the two endpoints, gamma a equals to y and gamma b equals to z, are fixed, and you vary all possible gammas that are available there. And again, for simplicity, we assume that that gamma is a continuous and piecewise C1 curve. So this I is called the admissible set. Okay, so this I is called admissible set. And later on, we're gonna make this set more general. For now, it's just a set of curves with two fixed endpoints, y and z. And those curves are always continuous and piecewise C1. And you see that we have a fixed length here, just from A to B. I mean, not length of the curves, but length of the parameterization. Okay, so we say that gamma in this admissible set is a minimizer in this class I, if I of gamma minimize the action. Okay, it's just a very simple problem in calculus of variation. Again, if you have done that, just enjoy it. If you haven't done that, just think about the fact that for a particle, or for, let's say that a person to go from y to z, within the parameterizations between a and b, then that person tried to minimize his or her own action. Okay, and we, as always, as a first law of physics, or like always, a natural problems first do is to find a minimizer, the one that minimizes our action. Okay, so also later on, that we're gonna deal with general curves, gamma, that are absolutely continuous, but also we're gonna deal with curves, that are, not just from a fixed interval AB. That's not enough. We're gonna deal with curves like map from -infinity to 0 to the torus, or curves that mapping from 0 to infinity to the torus, and or curves mapping from R to the torus, and then we're gonna care about the the dynamics of gamma at plus minus infinity. So that's going to be a more modern viewpoint, because if you fix the interval, and if you only have the problem in a fixed length, and everything is rather classical. As I said, we're going to study about existence and regularity of such minimizers. But then the modern viewpoint is going to be, we care about the curves that have like the behavior at infinity, how they're going to behave. Can we study about the large time behavior of the curves, and can we study about the ergodicity of the curves? And that's going to be really about dynamical property, but that's later. Okay, so for now, we're going to prove our first theorem. So the thing is the following. So the first result, the first theorem is going to be about that if gamma in situ is a minimizer, then gamma satisfy the so-called Euler Lagrange equations. Okay, so that's the first diagram. I drew it here so that you can compare the results later on, and you can see that we would need to assume more here. I'm assuming that gamma is C2. As I said earlier, we only have that the class of admissible functions are only, or curves are only piecewise C1, right? But here I'm assuming a bit further that if gamma is C2, so it's smooth enough, then I can prove that it satisfies an Euler Lagrange equation. Okay, so you see we are doing step by step. by assuming a lot, and then we're going to reduce assumptions more and more until we get to the thing that is optimal. Okay. So the set of assumptions are pretty much like what we end last time. You assume that L is CK, L is superlinear in V and uh, convex, locally uniformly convex in V as well. So that's pretty much the set of assumption that we would like to have. So the Euler-Lagrange equation says that if gamma is C2 and is a minimizer in this class of admissible functions, then I would have that gamma satisfy the following Euler-Lagrange equations from A less than equal to T less than equal to B. Okay, the way to think about that is that you would take the derivatives in both of the variables, right? So you have L of gamma T, gamma dot T. So I would, to think about the Euler-Lagrange equations, I would take the derivative in both variables. If I take the derivatives in the V variables, I would have, something like gamma dot pops out, right? So I have one derivative more than the gamma. So I would have to hit it back. That's why I have d over dt. So that's the way to think about that. Because again, I have one more derivative, right? Instead of gamma, I have gamma dot. So I have to hit it back. That's why I have d over dt of dv. And when I take the derivatives in x, so dxl of gamma t, gamma dot t, then if I hit the derivatives in x, then I just have gamma, right? So it's the same thing. That's why I'm not getting anything. So that gives me the Euler-Lagrange equation, and this happens for all a less than equal to t less than equals to b. So that's our Euler-Lagrange equation. Okay, again, this is quite natural for those of you who have done this. Again, just enjoy it. The proof is so the proof of this is sort of a classical method of calculus of variations. Uh, Classical method of variations. Let's just say variations. Okay. Again, you can think about the problems in two ways. You can think about the problems in the abstract way. And let me say about the abstract way first. The abstract way is that you have I gamma is equal to the mean of I of eta for eta in the class of I, right? So the abstract way is that gamma is the minimum point. So you from here would deduce that the d of I of gamma equals to 0. Okay, but again, this is a functional, right? So I maps from the space of functions to the reals. So what is the meaning of this? And if you want to talk about the meanings of this, and you would have to talk about Gatto's of Fresher derivatives and stuff like that, right? Uh, but I mean, on the other hand, you can view about the problems in a more, in a simpler way. That instead of thinking about the abstract derivatives, you can think about the problems. In fact, that if you do variation techniques, that it's going to give you back to a normal problems, just maps from R to R. And again, I mean, let me record quickly here. So again, enjoy it if you have seen it. So the idea is to do variations, so calculus of variations. And what you do is that you take any possible curve eta smooth, where you have eta A equals to eta B equals to 0. So you take any smooth curve, but with 0 endpoints. Why do you need 0 endpoints? Because then if you take gamma plus S eta, it's going to be always admissible, right? So again, so this one implies that gamma plus S eta at A equals to Y, and gamma plus S eta SB equals to Z, because you are not changing the two endpoints. So by fixing the endpoints of eta to be 0, when you take gamma plus S eta, it's going to be always admissible. So that's simple. So here I drew a little cartoons about variations. Essentially what you do is that you're going to vary S eta, right? So, you can, if S is big, then the variation is going to be like that, and you're getting smaller as S getting smaller, and eventually you're getting, when S equals to 0, S equal to 0, then you get back to exactly gamma. So that's the variation techniques. The idea is that you're mapping from a space of curves, which is complicated. But if you do this variation techniques, you're only doing the variation in, so only variation in S in R. So that's why it's a very useful techniques, because you are switching from a complicated problem to a problem of one parameter. Sometimes you can do more, sometimes you can do 3-4 parameters depending on the problems. Okay, so so that's the techniques. And when you do that, you can define IS to be little I of little s to be the action functional of gamma plus S eta. And here you can see that, when you do that, then you can see that I is now functions mapping from R to R. So that's a key point. Instead of dealing with complicated Frechet or Gato derivatives in an abstract function space, you now can just deal with I, the variation, which is a functions mapping from R to R. So this is simpler to deal with. Again, I mean, this is very simple, but you can see that most of the fundamental ideas of mathematics are like that. Once we understand it, they're very simple. Okay, so if you do that kind of variations, you can see that I of 0 is the minimum of I of S, right? Because at 0, I of 0, of course, at 0, I of 0 is I of eta, right? And it's less than equals to I of S, which is I'm sorry, it should be no, gamma. It should be I of gamma. Uh, I of gamma, which is less than equal to I of S, which is I of gamma plus eta S. No, S eta, right? Because gamma is a minimizer. So whatever the parameters you are doing, I of 0 is the minimum value. Hence, again, by normal calculus technique, as you have, again, I is mapping from R to R, and you have I of 0 is the minimum of I, S for S in R, right? So once we get to one dimension, it's easy. Or sometimes you can do variations with some parameters. So you transform the problem from infinite dimensions to a problem of finite dimensions. And that's also simpler to do. So clearly from here, you would have I prime of 0 is 0. Okay, and that's it. That's the whole method of calculus of variation, nothing more than that. Okay. So of course we need to compute what is I prime of S, right? And that's the whole thing. Well, I mean, again, we assume that everything is C1 or piecewise C1 here. So when you do computations, you can just see that S occurs here and here. So when you differentiate, you can just differentiate inside the integral, right? Everything is okay here. We are just doing Riemann integral here, not even Lebesgue integral. When you differentiate in the first lot here, then you have dx of L, right? Multiply with eta. So that's exactly that, right? And then when you differentiate in the V slot, you have dv of L multiply with, you differentiate S eta dot in S, so you have eta dot, right? So that's that, you know. Um, so again, it's simple. It's exactly that techniques of calculus of variation. And the good thing when S equal to 0 is that the integral simplified, right? You know, when at 0 you have this is that, and then you just have dx of L of gamma gamma dot. So there's no eta anymore. The variation goes away. So just dx of L eta eta dot dot with eta, and dv of L of gamma gamma dot dot with eta dot. Okay, and now you see that you have the eta here and eta dot here. Clearly that we would want them to be in the same page so that we can see them as test functions, right? And here's is where we use, so here's the place we use the fact that gamma is C2 here. Okay. Why do I need to use the fact that gamma is C2 here? I'm doing integration by parts, right? So eta at the two endpoints is 0. So when I do integration by parts, I don't have to, take into the account the values at the boundary. And that's also the good thing about calculus of variations is that, we typically can ignore the boundary value. And you can see that this is true for, I'm sorry, when I kick the derivatives, eta dot here to eta, so then that means that I kick d over dt to the dv, right? And that's exactly when I explained about the way to think about Euler-Lagrange equation is exactly that. So so you have 0 equals to this integral, and you have this whole thing here. Um, uh, you know, multiply with eta is equal to 0 for any test functions eta. So that means that you have the thing inside here has to be 0, right? And that's exactly our Euler-Lagrange equation. Okay. And nothing more than that. And as I said, we had to use the fact that is C2 because we would want to make sense of this derivative. Okay. And in fact you can compute, so remark here, you can also compute explicitly what's going to be this term. It's not, it's not too, how to put it, it's not too nice, but it's computable. You just differentiate in t. So differentiate the first time, you have dxv d square xvl gamma gamma dot multiply with gamma dot, plus you differentiate twice in L, you have d square vv L gamma gamma dot gamma double dot equals to dxl of gamma gamma dot. Okay. So if you differentiate, you have that. And remember that d square of L is invertible, right? Because that's the assumption we put. So from here, you can actually write down gamma double dot equals d square v. Sometimes I would write d square v only, but sometimes I'm careful. I'm write out d square vv L inverse multiply with dx L of gamma gamma dot minus d square of xv L gamma gamma dot gamma dot. Okay, and that's essentially the other way to write the Euler-Lagrange equation. Okay, does that make sense? So this is one of the reasons why we would need to require that gamma is in C2 in this derivation. Okay. So now I said this one last time, but let me remind you why it was important. So before we move on to the next step, so so connection again between Euler-Lagrange equations and Hamiltonian ODE. I mean, surely we're gonna recall this one a lot more later on, but for now, I don't want us to go and get missed. So everything I want to say everything clear here. So again, the Euler-Lagrange equations reads that d over dt of dv L gamma t gamma dot t equals dx of L gamma t gamma dot t. And let me recall that gamma t here is surely, I'm going to denote it by xt. This is position of our particle. Okay. Gamma dot t, sometimes people would denote it to be vt. This is the velocity of our particle. Okay. And you can see that many times, in the literature, in physics, in fluid mechanics and others, when you record the gamma gamma dot, so gamma gamma dot, or denoted by xtvt, is typically called the Lagrangian viewpoint or Lagrangian coordinate. So whenever you see a talk in fluid mechanics or others, when they say about Lagrangian coordinates or Lagrangian viewpoint, this is that. Okay. And then remember that uh, earlier we already talked about the duality, right? So duality, we have that pt is dv of L gamma t gamma dot t. This is the momentum. In classical mechanics, then P is m times v, and in that example is that. But in general, for general Lagrangian, this is a generalized momentum. Okay. So this is the momentum variables, and again, xt is nothing but exactly gamma t. Again, this is position. And okay, I need to make this smaller. And you can see that whenever people talk about xtpt, so this is going to be the Hamiltonian coordinate or Hamiltonian framework. So I mean, you often see that in many talks we'll say that you can go between Lagrangian and Hamiltonian frameworks, and sometimes it's more convenient to use this and sometimes it's more convenient to use the other. So that's just different setting. Okay. So from here, we can write out what is going to be our Hamiltonian ODEs. This is x dot t. X dot t is nothing but gamma dot t, right? And gamma dot t. Sorry, what did I want to say? Hold on a second. I'm making. No, that's correct. I'm sorry. X dot t is gamma dot t, and is exactly dph of xt pt. Okay, why? Because of this duality, right? Have p is equal to dv, right? So when p equals to dv, then that means that gamma dot t is equals to dp, right? Because that's exactly the duality. Okay. So this link with that because of the duality. Oops, this is not good. This two things because of the duality. Whenever equality happen, then when p equals to dv, that means that v equals to no, p equals to dv, then that means that v equals to dp. So that's correct, right? This is exactly the velocity. X is the velocity of the particle, x dot, right? And then second of all, you have that p dot t, as you have earlier, p dot t is exactly, so this is pt, right? So p dot t is d over dt of pt, and this is given to us by the Euler Lagrange equation. This is dx of L of gamma dot, but also by the property we proved last time, dx of L is minus dx of h of xt pt. Okay, so that leads us to the Hamiltonian system of this form. Okay, and as I said, we're gonna revisit this point many times, and then we're gonna link it to Hamilton-Jacobi equations through this platform. But I'm keep repeating this so that we see that everything we have developed so far is correct. Okay, not correct, but in a correct platform. Okay, let me know if you have questions. All right. So now let me do one more results for today. So here I put a box up here that we show that if gamma is a C2 minimizer, then it satisfies the Euler-Lagrange equations. We had to assume that it's C2 because of the step here that we do integration by parts. So that's why we need it. So the second result for today that we're going to prove is that if gamma is C1, is a minimizer, then we also imply that gamma is ck. Again, k here is the k given greater or equal to 2 in our problem. And also, clearly when gamma is ck, then gamma also satisfy our Euler-Lagrange equations. Okay, and that's the second result. So you see that, we are relaxing things, right? Because assuming that I have a minimizer in C2 is too much, it is more reasonable to assume that I have a minimizer that is sort of less regular. Okay, so that's the result. And to do that result, I would need this remark. So if I only have that gamma is C1, then in this one step above here, in this step here, I cannot do the integration by part, right? Because I cannot do d over dt of dv. I don't know that one is C1 to differentiate it. So if I don't know that, then I wouldn't be able to kick the derivatives to eta, right? So then I claim that I only have then that I have dv of L is equals to this integral plus a constant q. Q is a constant vector. Okay. So again, you can check this one. So I would like you guys to discuss and check this one for fun. But what I meant here is that instead of kicking the derivative to eta, then I would write out something like integral from a to b dvl gamma dot plus integral from a to t dxl gamma dot ds multiply with eta dot dt equals to 0. So that's what I have. So instead of kicking the derivative to eta, I'm sorry, kicking the derivatives of eta dot to d over dt, what I'm doing here up here is that in this integral, in this term, in this integral up here, the one in the red box, I'm trying to put the derivative to eta dot so that I have everything is in the same page, right? So if I have the derivative in eta dot, then I would have this thing happening. So that what I would expect to have. Okay. But then from this result, integral of the thing in the box multiply with eta dot dt equals to 0, then that would allow me to imply that the thing in the box is a constant vector. And so that's why I have, from here I have this conclusion. Okay, so you see that I can't yet differentiate in dvl, but on the other hand I can integrate dxl, and that's what the relation I have. Okay, and that's the key thing that's gonna allow us to do our result. Maybe let me copy it down here. I mean, you're gonna see that we need the thing that dvl of gamma t, gamma dot t equals q plus integral from a to t dxl of gamma s, gamma dot s ds. Okay, so this is the thing we need. Okay, so let's do our proof to end our lecture now. We have that it gamma is c1 and it's a minimizer, then we claim that it's c2 or ck, and also from there it's automatically satisfy the Euler Lagrange equations by the above theorem. Okay, so the way we do that is that we recall the previous ck minus 1 diffeomorphism result we have. So recall that if I fix any point here, I fix the x naught v naught to be the position and the velocity at the point t0. Okay, so and I recall that the map xv that maps to x dv is a local c1 diffeomorphism, right? So if it's a local C1 diffeomorphism, then you can always find its local inverse, and you have there's a k is the inverse. So what you have is that you have k is ck minus 1, and k is the inverse map. So k of x not dvl is x not v naught. And locally k of gamma t, maybe this is a little bit hard to see, k of gamma t dvl of gamma t gamma dot t equals to gamma t gamma dot t for t near t naught. So by this I mean that for for t minus t naught less than epsilon or something. So that's fine, it's just a local result. To prove differentiability we just need local results, right? So that's good. Okay, so I recall what we needed here. So this is the key point that we need in our proof, right? So what's the key? You see that dvl is at least c1, right? Again, we are being careful here. Why is it at least c1? Let's see. You know that gamma is c1. So gamma is c1. Oops, not that. So you have gamma as c1, gamma dot is continuous, right? So this is c1, this is a continuous function. So the whole dxl is a continuous function, right? And you're taking integral from a to t, so you're smoothing it up. So basically from here you imply that dvl of gamma dot is c1, because it's the antiderivative. It's an antiderivative of a continuous function, so it's c1. And k is ck minus 1, and this also answered the question some of you have earlier. I always need to have that k minus 1 is greater equals to 1. It's just a technical reasoning, but that's that. So clearly you have what? You have k composed with gamma dvl of gamma dot equals to gamma dot, right? So you just see that you have k is at least c1, gamma is c1, dvl is c1, right? So you are composing two c1 maps. that gives you that gamma dot is C1. Okay. Yeah, so you have gamma dot is C1, and that implies that gamma is C2. And again, you can do iterations, induction, that's not hard. You can prove gamma is CK. Or you can actually write out, if it's C2, you can write out the Euler-Lagrange equation and imply that it's CK by induction rather easily. Does that make sense? Okay, so that's that. I think that is quite clear. Um, so so next time, of course, I'm gonna send you the lecture. I'll need to check it and figure out what I want to do. So next time we're gonna reduce the assumption on gamma, and we also gonna also try to have existence of minimizer, but I mean and so on and so forth. But so far you can see that the flow is rather clear, right? The calculus of variation problem is very clear, and that's a very interesting problem to study. It's fundamental. We haven't touched the fact that whether the problem has a minimizer or not, and we are not sure what is the regularity of our minimizer. Okay. Nevertheless, we have shown that if it's C2, then it satisfies Euler-Lagrange equation. If it's C1, then it's still satisfying Euler-Lagrange equation, and it's the minimizer, in fact, is CK. So for example, but however, you see that the earlier class of functions, like I define gamma in I, this is just a set of piecewise C1, right? So what if I only assume that my minimizer is piecewise C1? Can I prove that it's CK and also satisfying the Euler-Lagrange equations? Or even if I reduce it more, right? If my curve, my minimizer is only absolutely continuous and whether it's CK. It's turned out it's the case. We're gonna prove it. So, we're gonna prove that actually um, every minimizer is smooth enough. But there's a catch that we would need to assume that, everything is nice. Our Lagrangian is uniformly convex and is smooth enough. Uh, in fact, there was a fun story that uh, not fun. I mean, there are many interesting counterexamples in the literature. I'm not an expert in those counterexamples, so I cannot say for sure. But okay, maybe a remark is that if L is not nice, then minimizers can have bad regularity. Okay. And this is a very important remark. We assume that L is very nice. It's CK, is uniformly convex or locally uniformly convex. But if it's not nice enough, then there have been counterexamples in the literature. I think people care about it because it's related to elasticity, and I'm not keeping up to date with those counterexamples, but I'm sure that there are many. Some examples from John Ball and others, and last year or 3 years ago, I don't remember, one of my students encountered this kind of issue, and it turns out that there was some papers in the literature that they are not careful. They can just say, oh, I have a minimizer, so it's CK. But he could point out a counterexample that if L is quite badly behaved, so if it's only BV or something like that, if L is only BV, then you can have minimizers that don't satisfy the Euler-Lagrange equation. So minimizers can have bad regularities, and minimizers might not satisfy Euler-Lagrange equations. So we have to be careful. So that's why we're going to spend quite some lectures on this and try to get really deep into the key points. Okay. Uh, any quick questions? Is the speed okay for you guys? Or is it too boring, or is it, I don't know. Okay. Yeah, again, I mean, I'm trying to not making us lost. Also myself not getting lost. So thanks a lot for being patient with me if I'm doing it slowly. But other than that, it's great. You know, again, stay safe and healthy, all of you, and I'll see you on Friday. Okay, so see you. Bye for now.